I think this series of lectures will be really about the basics of black holes. So we're going to have to first of all learn what black holes are and look at the geometry of some simple black hole spacetimes. In fact, all of the ones that you can construct that are asymptotically flat. Then we'll move on to the question of, if there is time at least, gravitational collapse and why it is that it actually must happen. A very brief discussion of the singularity theorems. Then the laws of black hole mechanics, the Hawking process, and at the end of it, a little bit about black hole hair and the soft theorems. So I hope we can manage to get through all that material. Firstly, I think the thing to do is to set our conventions. So my metric signature is going to be minus plus plus plus. My conventions for curvature are the same as to be found in Hawking and Ellis and Misner, Thorne and Wheeler and many other places, but not everywhere. So that the covariant derivative, when commuted acting on a vector field, is going to be just RABCD BD. The advantage of writing it this way is that the indices go in the same order on the covariant derivatives as they do on the Riemann tensor. The Ricci tensor, for me, is found by taking a contraction on the first and third index of the Riemann tensor. The Ricci scalar R is going to be GAB times RAB. And lastly, the Einstein equations are just going to be RAB minus a half of R GAB equals 8 pi times Newton's constant times TAB. I will usually use units such that G equals C equals H bar equals Boltzmann's constant equals 1, usually. But I put the big G in here just to keep track of things. The Einstein equations can, of course, be derived from an action principle. And the action that we will use is I equals 1 over 16 pi G integral of R square root of det G d4x, the Einstein-Hilbert action, and that will be supplemented by any kind of matter action, integration of L matter. This will be a Lagrangian density, so there will be no square root of G sitting in there. The energy momentum tensor with these conventions is just going to be TAB is equal to 2 times the variation of the matter action with respect to the metric, and then there will be a square root of minus G to get rid of, to turn it into a tensor. So that defines how various signs of things will work out for us. When dealing with the action, there is, however, a subtlety with the Einstein-Hilbert term. The Einstein-Hilbert term you usually think of as being something over all, integral over all of the space-time, which we'll call M. But typically, when one varies the action, you forget about boundary terms. You just throw out whatever you get on the boundary. And whilst this doesn't matter when you're deriving the Einstein equations, the question of boundary terms will become important at some point, so I just want you to keep that in mind. There are various other fields that we will encounter in what we're doing. We'll come across scalar fields. And so the Lagrangian for scalar fields will be square root of minus G, and then there will be a factor of minus a half dA phi dB phi GAB minus a half m squared phi squared. You'll notice the signs here is such that with my sign conventions the kinetic energy term here is positive. If we're interested in electromagnetism, the Lagrangian for that will be the square root of minus g FAB, the Maxwell field strength tensor, and then a 1 over 8 pi to prevent various other numbers becoming unmanageable. So that's really, I think, the only things that we're going to be directly interested in the near term. FAB, of course, is just equal to the skew derivative of the vector potential. So I think that's really all I want to say about conventions. Now let's start something more interesting. The first place that I want to look at is actually Minkowski space. Minkowski space may seem to be a rather trivial place to start, but it actually illustrates an enormous amount of things that are going to be relevant to what comes next. And in particular, we're going to use this as a sort of template for dealing with other more interesting space-times. So let's start off with Minkowski space in polar coordinates. So it's just minus dt squared plus dr squared plus r squared d theta squared plus r squared sine squared theta d phi squared. So the first question you might want to ask is, where is the origin and what significance does it have? Well, of course, the origin here, r equals 0. Could have really been put anywhere in the space-time, because the space-time is flat and hence maximally symmetric. All points in this space-time are equivalent. Another way of saying that is that Minkowski space has the maximal number of killing vectors, namely 10. So that is to say that if you took this equation, the killing equation, you would find 10 solutions of it corresponding to 4 translations, 3 being space-like and 1 time-like. There would be 3 rotations and 3 Lorentz boosts. If you take these killing vector fields, of course there will be 10 of them, let's call these psi I, and you looked at the algebra of these killing vectors, that is to say, you would take the commutator of these things, psi I, A, let's not write it that way. Take the Lie derivative of psi I, of psi j, minus Lie psi j psi I. This will be something like 2 c I j k psi k, and these would be the structure constants of the algebra corresponding to the Poincare group. So those are the 10 killing vectors in Minkowski space. Associated with each killing vector, there is in principle a Noether charge which we could call Qi. That will be the integral over some 2 surface of something like del A psi b for the ith object, anti-symmetrized. I haven't specified what this 2 surface is yet, but you need to determine which 2 surface is going to be relevant for determining what these charges actually are. So that's sort of a common theme associated with all symmetries. So that's really the sort of local geometry of Minkowski space. But really when one's considering black hole spacetimes, you want to consider all of the spacetime. This is a sort of local picture of what's going on. And really what you want to do is look at all of Minkowski space, not just a little bit of it given by the infinitesimal line element. So let's start trying to do that. Let's take any point in Minkowski space, which may as well, of course, be the origin. Call this point P. Then one way of trying to understand the global structure of Minkowski space is to consider the light cone of the point P. So the light cone of the point P divides space-time associated with point P into a number of different regions. So the light cone of P looks something like that. If you start off at P, you could be inside the light cone to the future. Where you could arrive in a time-like direction. Or you could be here, past time-like direction. You could be on the light cone itself, corresponding to future-directed null, or on the light cone in the past, past directed null, or you could be space-like separated from P somewhere out here. There is some notation that comes with this. The chronological future or past of the point P, usually called I plus or minus of P. This is the chronological future with a plus or past with a minus of P. It's a set of all points that you can reach in a past or future directed time-like direction. Similarly, there's what's usually called the causal past and future of the point P. Usually written J plus or minus P. And this is defined in exactly the same way, except that it now means time-like or null separated from the point P. So what that means is that the causal future and past really defines what can influence the point P, or what the point P can influence in the space-time. So it's a way of describing how various things can influence each other in the particular space-time. These ideas of the chronological and causal future and pasts don't just apply to Minkowski space, but of course you can use these ideas for any point in any space-time you care to think of. And indeed, that's what we're going to do. We're going to consider what these various sets look like in various space-times. You can also, of course, do something a little more general than this. Instead of taking the point P, you could imagine considering a set of points. So you could imagine S as being the union of a collection of points Pi. Then you can define the chronological past or future, the causal past or future of S as being equal to the union of I plus or minus Pi or J plus or minus Pi as appropriate. So you can deal with whole sets of points in that way. So, for example, let's think a little bit about what one tries to do in any physical situation. Suppose that we're in Minkowski space and we're interested in trying to do physics, and so here is some space-like surface in Minkowski space. And you're interested in asking how would you figure out what happens at some point P in the space-time here? Well, what you would do is you would say only things in the past light cone of the point P can possibly influence what happens at the point P. And so if you want to work out what happens here, you need to specify things like initial data, the values of fields and their first derivatives on this surface inside the light cone. So you don't care what happens over here, and you don't care what happens over here. You're only interested in what happens in the middle. So in order to determine physics at P, it only depends on J minus of P. That's just a statement of causality. So, armed with all of this, let's try and think a little bit about how one would describe the geometry of all of Minkowski space. The trouble with Minkowski space is that it's very large. And that obscures some of the key physical points of the space-time. So one typically deals with the issues of what can influence what in Minkowski space by performing a conformal transformation to make it of finite extent. So let's think a little bit about conformal transformations. these are just basically taking a metric, GAB, and constructing from it a new metric of the same signature by multiplying it by just some overall factor. So I've written it in the form omega squared because I want the thing to keep its Lorentzian signature. Omega is usually taken to be real and non-vanishing. Under a conformal transformation, you know that, well, whatever is a null in the metric G is going to be null in the metric G hat. So this conformal transformation preserves the light cone structure of the space-time. And similarly, you can see that time-like and space-like are also preserved. But conformal transformations have some other nice properties. They also preserve null geodesics. So a geodesic in G hat that is null remains a geodesic in G. I guess it should be the other way around. So that's a nice property of geodesics. I guess you've probably done that particular problem at some point in the past. If you have not, we can work through it at some later point. However, time-like and space-like geodesics do not remain geodesics under the conformal map. So those are a couple of nice properties of conformal transformations. There's some other properties that make conformal transformations an enticing thing to do, and that is that some field equations are invariant under conformal transformations. That is to say, solutions of the field equations remain solutions of the field equations. So some examples. Electromagnetism. A quick way of doing this calculation is to observe that Maxwell's equations are DAFBC equals 0. This is vacuum equations. Of course, we know that you can replace this covariant derivative by a partial derivative. And another way of writing the divergence of something is just to rewrite this as 1 over the square root of det g, dA square root of det g, FAB equals 0. So to see that there's conformal invariance, just guess how A transforms. So A will go to A hat, but I'm going to keep that equal to A. What happens to the metric? GAB goes to GAB hat, which is equal to omega squared GAB. That means that the inverse metric, GAB indices upstairs, is equal to G hat AB. That's equal to omega to the minus 2 times the old GAB. The square root of det G goes to the square root of minus det G hat. This is a 4 by 4 object, so that's going to give you a factor of omega to the 8, omega to the 4th times the square root of minus G. So here, this is independent of the metric. So if A goes to A, nothing changes. So this is trivially okay. This one here, that's a bit more complicated. All we really need is for this thing to remain equal to 0. But that goes to dA square root of minus G hat. Now what happens to FAB? FAB with its indices upstairs meant GAC, GBD, FBD, FCD. So F goes with its indices downstairs goes to F hat AB, which is just this. So this goes to F hat AB is equal to G hat AC, G hat BD, FCD hat. And so you can see that this thing is going to be omega to the minus 4 FAB. So when we look here, what will happen is that this thing picks up a factor of omega to the plus 4. This thing picks up a factor of omega to the minus 4. And so the two things cancel out. So that if A is a solution in one conformal picture, A hat is a solution to Maxwell's equations in the conformally related space-time. It also solves Maxwell's equations. In G hat AB. So that's an example of a set of equations which are conformally invariant. You'll notice immediately that this only works in space-time dimension 4. If you change the space-time dimension, you won't change how F upstairs changes, but you will change how det G changes. That will pick up an extra factors of omega, and it won't work. Similar considerations apply to any form field, so that scalars are typically invariant in dimension 2. Two-form theories that give rise to three-form field strengths work in dimension 6, and so it goes on. But I'll leave that up to you. There are some other equations which are conformally invariant. Let's look quickly at what they might be. Scalars. Well, scalars with the conventional just minimal coupled action are not conformally invariant. However, so if you took this action, various things ruin it. So the first thing that will happen is, of course, that the mass is going to ruin this thing. So you can't have massive scalars which are conformally invariant. However, this thing doesn't work either, because if you thought that this was you're going to try and make this work, let's look at the form of the action. It's minus a half del A phi del B phi GAB square root of minus G. Well, you can sort of see what's going to happen. Under a conformal transformation, this will pick up a factor of omega to the fourth. This will pick up a factor of omega to the minus 2. So the only way in which it's ever going to work is if phi goes to phi hat, which is equal to phi divided by omega. That's fine, but when this derivative hits this omega, of course things will get messed up and the action won't remain invariant. But there's a trick. Conformally invariant scalars can be made by looking at the following action: minus a half dA phi dB phi GAB minus 1/12 of R phi squared, and the square root of minus G. If you took this equation, or the equation of motion coming from this action, you'll discover the wave equation is equal to minus box plus 1/6 of R times phi. And if phi is a solution in metric G, then phi hat is equal to phi over omega is a solution in metric G hat. So this is sometimes called the conformally invariant wave equation. Something like this will work in any dimension of space-time. You will need to change the 1/6 into some other number. And you'll need to change the conformal weight of phi. So instead of being omega to the minus 1, it'll be something else. It's worth trying to prove those particular statements. So you can regard that as the first exercise. So you can always make conformally invariant scalars. There's something else that you can do with scalar fields. Somewhat amazingly, you can add an interaction term in dimension 4. You could add to this a lambda phi to the fourth, and it's still conformally invariant. but only in dimension 4. There's one other field that is conformally invariant, and that's massless Dirac fields. I don't want to try to prove that for the very simple reason that it will involve looking at the covariant derivative of spinors, which I suspect you may not have come across. Is that true or false? Who has come across covariant derivatives of spinors? Not many. If there is time, I'll try and deal with that on Monday. But I make no guarantees. So for massless Dirac fields in dimension 4, then psi goes to psi hat equals psi omega to the minus 3/2 gives you the conformal transformation properties. So that's it for the list of conformally invariant fields. Unfortunately, the Einstein equations are not conformally invariant, and neither are linearized gravitational perturbations. So, nevertheless, making conformal transformations in various spacetimes is a very useful thing to do. So let's see what happens when one makes a conformal compactification of Minkowski space. The reason one is doing this is just simply so that all of Minkowski space can be described in on a finite piece of paper, essentially. So let's first of all start off with the metric on Minkowski space. We've already seen that. It's minus dt squared plus dr squared plus r squared. And I'll write that as d omega 2 squared because this is just the metric on the unit 2 sphere. Now, the whole point of doing conformal transformations is to retain some knowledge, or gain some knowledge, I suppose might be a better way of putting it, of the causal structure of the space-time. So, if you considered the world line of some particle at r equals 0, t goes up in this direction, the way in which you would study the causal structure would be to construct a retarded time coordinate, u, which basically tells you where the light cone is. So let's consider u equals t minus r. So if this point is t equals 0, the future light cone of this point is just the line u equals 0. This is a rather two-dimensional picture. I can't draw 3 dimensions, but it looks perhaps something a bit more like that. This is usually called the retarded time coordinate. Similarly, you can construct an advanced time coordinate that labels the past light cone. Something like that. This would be the line v equals t plus r, and then the past light cone at this point would be v equals 0. But you could move yourself up this curve a little bit, say to this point, and then the red light cone would be u equals some other constant. And then the past light cone would be v equals some constant. And that would be true for all of the space-time. So a nice way of describing the space-time, if you're really considering what happens to some particular point in the space-time, would be to write things in terms of uv coordinates, not tr coordinates. So let's adopt this policy. V is going to be t plus r, advanced time. This is going to be, did I call this advanced time? I should really call V advanced time. And u is going to be t minus r. But remember that r is greater than 0, or equal to 0. And therefore v is always greater than u, or equal to u. T and r both run from, t runs from minus infinity to plus infinity. R runs from 0 to infinity. So the range of v and u is most simply described by saying that u has got to be greater than minus infinity, and this is going to be plus infinity. So those are the coordinate ranges of v and u. And I want to emphasize that they represent the labeling the light past and future light cones at some point based on the origin. So what is the metric in these coordinates? Well, it's kind of easy. You just simply look at this thing, and you'll see that you get dt squared minus dr squared is dv du. So ds squared in these coordinates is going to be minus du dv plus. Here we have an r squared. So r squared, well, r is just equal to a half of v minus u. So you get a quarter of v minus u squared into d omega 2 squared. And that's the metric in null coordinates. Now, of course, u and v run from minus infinity to plus infinity, which is awkward. So the simplest thing to do is to invent a p and a q, and I would like tan p to be equal to u. And tan q to be equal to v. So to reproduce the set of coordinates that we have, we would have that q has got to be bigger than p, or equal to p at the origin, and these things I'm going to define to run from pi by 2 to minus pi by 2. So that's a set of new null coordinates, but they take their values over a finite range as opposed to an infinite range. What is the metric in these coordinates? You're going to get a minus sec squared p, sec squared q, dp dq, from using du equals sec squared p dp, etc. And then this term here looks a bit more complicated and is equal to a quarter of tan q minus tan p all squared d omega 2 squared. At first sight that looks awful. But actually you see immediately that you can take out from here a factor of sec squared p sec squared q. So you're going to end up with minus sec squared p sec squared q. Right, let's put a plus there. Minus dp dq. And then, well, I'll cut out the algebra for you. You'll end up with a quarter of sine squared p minus q d omega 2 squared. Let me make sure I got that right. So now that looks like a conformal transformation on some relatively simple space-time, which we will investigate. So I want to call this the conformal transformation. You'll notice that at p and q is plus or minus pi by 2, this thing becomes infinite. It's this infinity that is effectively brought in infinity in Minkowski space to some finite point in this space-time. And it's a finite place in this metric in square brackets. So since all we're interested in is the causal properties of the space-time, we can just forget about this term here and just look at the thing in brackets. The conformal structure of the thing in brackets will be the same as the conformal structure of Minkowski space. Except now we're just looking at some finite region. So what is this finite region? The easiest way to understand this is to go back to looking at a sort of time-like coordinate and a space-like coordinate. So we can define p to be equal to t hat minus r hat, q to be equal to t hat plus r hat, in which case we can rewrite this thing in square brackets in the following way. It's going to be, where's the eraser? Minus dt hat squared plus dr hat squared plus 1/4 of sine squared 2r hat times d omega 2 squared. So that's a new line element of compactified Minkowski space. So what is this a metric of? Well, whatever it is a product space-time, because there is time here which decouples from space here. So it's something with topology of R cross something. But if you look at this thing here, you'll immediately see this is just the metric on the unit 3 sphere written in hyperspherical coordinates. So this has the topology of R cross S3. This thing here is the metric on S3 in hyperspherical coordinates. Does this need further explanation? Right. Those who think it does not need further explanation, put their hands up. It seems to me that it does need further explanation. So, let's see if I can get this right. One way of thinking about a 3-sphere is the surface a squared plus b squared plus c squared plus d squared equals 1 in R4. This hyperspherical coordinates are basically the same as polar coordinates for the sphere and so what you need to do is to introduce a set of angles, and this set of angles is related to A, B, C and D in the following way. Now I have to get this straight, and because of the danger of factors of 2 errors. So this thing would be cos 2r hat sine 2r hat cos theta 2r hat sine theta cos phi sine 2r hat sine theta sine phi. These two could be swapped around if you like, but if you do things in n dimensions, typically you do it in that way so that it becomes clearer how you generalize hyperspherical coordinates. And that reproduces the unit sphere. So this gives you the hyperspherical coordinates mapped into Cartesian coordinates in R4. So let's continue with our exploration of this metric. It is a deeply unfortunate fact that I cannot draw things in dimensions greater than 2 easily. That's just one of my limitations. So my S3 is going to become a cylinder. And so a picture of the TR plane looks like this. So I'm going to put this line to be r hat equals 0. And this line here is going to be r hat is equal to pi by 2. And t hat goes up like that. So what does this space-time look like? Well, it looks like a sort of diamond-shaped region. Here is the point P equals Q equals minus pi by 2. So that's the sort of boundary of space-time where the original t goes to minus infinity and r is equal to 0. The portion of the space-time that lives with p and q lying in the irrelevant region in between pi by 2 and minus pi by 2 corresponds to a region that looks like this. It starts off at this point here. This is really the light cone of this particular point and goes to the back of the cylinder that looks like that. And then similarly, this is the point P equals Q equals pi by 2, and its past light cone looks like that, and then it is on the back of the cylinder. So in terms of this picture, Minkowski space has been mapped into the region on the front of the cylinder, which is shaded in red. And on the back of the cylinder, let's see if I can get this right, it will be shaded in a hideous lime green color, and it looks something like this. So it's part of R cross S3, not all of R cross S3. In practice, nobody ever draws it like that. It's just simply, it's done this way because it sort of makes it clear what the meaning of this three-dimensional metric is. What you always do in practice is to flatten it out. Instead of drawing it on a cylinder, just draw a two-dimensional representation of it. The easiest way to draw it is the following. Let's make this line here to be r equals 0. Then you construct a region that looks like this. Each point in here is a two-sphere. this line here corresponds to this line here. It's the past light cone of this point. Let's give this point a name. T is infinity there, r is equal to 0. That means that it's where you end up if you let time go to infinity, but you stay at r equals 0. So it's, if you like, future time-like infinity. Sometimes called I plus. So this point here is I plus. Similarly, this point here is r equals 0, goes to minus infinity. So this is sometimes called past time-like infinity. Or I minus. Let's give this a label minus. If you went to infinity in a space-like way, that is, say you fixed t to be finite and r went to infinity, then you'd end up at this point here on the back of the cylinder, sometimes called space-like infinity, where you will discover that P equals Q equals R is infinite. P equals minus pi by 2 and Q equals plus pi by 2. So this is R infinite, T finite. And I guess I'm not supposed to write beyond here. Sometimes called I is 0. This line here you can think of in some sense as being the future light cone of past time-like infinity, and is sometimes called scry minus, past null infinity. This is the the past light cone of I plus, sometimes called scry plus, future null infinity. So all you've really done is you've unwrapped this red and green region here and turned it into this, and you've basically sort of folded this thing over so that you've only considered, you've identified this half with this half, so that it's just simply something which looks like that. This thing is sometimes called a Penrose diagram. It's a little unfair as a name because it was invented by Carter. Penrose was a much better artist than Brandon Carter. Well, actually, he still is. He was able to draw these things so they actually looked as if they were objects in a higher dimension. Carter's contribution was to put it into a picture where I could draw it, and not just someone skilled being able to draw it. To understand what the power of this construction is, let's get rid of this for the time being. We don't need this one again. And ask ourselves, what do geodesics look like in the Penrose diagram? Null geodesics, Well, I'm just going to consider what happens in the TR plane. So I'm going to fix theta and phi. These are angles on the two-sphere. That doesn't make much difference because many of the spacetimes that we're going to be considering are spherically symmetric. So let's look first of all at time-like geodesics in this picture. All time-like geodesics start at I minus and end at I plus. So that here is a collection of time-like geodesics which correspond to R equals a constant. You can also ask yourself about curves such that t is constant. I think that should really be green. And theta and phi constant. These will be surfaces that look like this. So that you can see that if t goes to infinity for fixed r finite, you will always end up here. And if t goes to minus infinity for fixed r finite, you'll always end up down here. If you go to space-like infinity, that corresponds to r going to infinity for t finite, you'll always end up at I0. But the important point to realize is that all time-like geodesics end up at either I minus or I plus, depending whether you're interested in the future or past endpoint. There is, however, of course, something which is kind of obvious when you think about it. If you're watching some kind of scattering process or watching some astronomical process, of course not interested in what happens at time-like infinity, you watch it. That means you communicate with things in the interior of the space-time by looking at it. And if you look at it, you're going to use null geodesics classically to do that. Null geodesics in this picture correspond to lines which look something like this. There'll be straight lines. They've been designed to lie at 45 degrees to the vertical or horizontal. Actually, null geodesics do this. So they're simply straight lines that look like this. Null geodesics end at scry minus or scry plus, depending whether they're you're going to the past or the future endpoints. There is an important issue here. Let's suppose that you start off at some point on scry minus, given by some angle on the celestial sphere. Call it theta and phi. You can watch a null geodesic. It goes through the middle of the space-time, then comes out, and emerges at scry plus. But it's not at the same polar angles. It's now at the antipodal point, on scri plus. Was the antipodal point to theta and phi, but now on scri plus. So these were on scri minus. In terms of conventional polar angles, that means that the theta will be here, it will be pi minus theta, and the other polar angle will be phi plus pi. And that's kind of obvious. It just simply says that if you put in a null ray in some direction, it's going to come out at the opposite point on the sphere. All null geodesics end on scri plus and scri minus. So if you're watching some kind of interesting process in a space-time, then something interesting could be happening here. But if all you're doing is watching it, then effectively what you've got to do is to construct a map between scri minus and scri plus. So all scattering processes That's true if you watch it, in other words, if you use massless states. But it might be there's some particles down here, or some astronomical object, similarly here and here, which move along time-like lines, so you have to include I minus and I plus in general. So that's a sort of general feature of how things behave in Minkowski space. So I will always draw the Penrose diagrams of Minkowski space this way. Sometimes people draw them as a whole diamond, but I'm not going to do that. Typically one thinks of Minkowski space as not being involved in any kind of horizons, but that isn't really true. Let's consider the following. This is an example of a horizon, but an observer-dependent horizon. We pointed out at great length that geodesics end at I minus and I plus for time-like geodesics. But that does not mean that all curves that are time-like end on I minus or I plus. So let's consider what happens to a time-like object that suddenly starts to accelerate at a constant speed, constant rate. So let's suppose that at t equals 0 it starts to accelerate. What happens to this unfortunate observer? Well, up till t equals 0, it just simply goes along here. Then it starts to accelerate. And of course, at some point, that means that relative to the origin, the velocity becomes asymptotic to the speed of light. And so it looks something like this. So that's the trajectory of such an observer. This observer has a horizon. A horizon is defined by regions of the space-time that this observer cannot see. So if you think about what this observer can see, Once they get to null infinity, that's where they sort of get to the edge of the space-time, they can only see in their past light cone. So that means that they cannot see this region of space-time. This is sometimes called a horizon because you can't see over it. And in this particular case it's called the Rindler horizon because it's associated with continuously accelerating observers. So another way of putting it is that the horizon corresponds to the boundary of the causal past of this particular observer. So he reaches, or she reaches, scri plus at the point P, then the horizon is equal to the boundary of the causal past of the point P, where P sits on scri minus where this observer ends. Again, I want to emphasize that if you are watching what happens in a space-time, you do it from scri. You do not do it from I0, and you do not do it from I+. If you're watching something, you are inevitably looking using photons or light rays or something, which means that you look at null geodesics probing the interior of the space-time. So observers are here. They are not here, and they are not here. So this is a fairly trivial example of a horizon, but nevertheless it's a prototype of what happens. So much for Minkowski space. Let's move on to some black hole spacetimes. The place one always starts is with the Schwarzschild metric. Its line element looks a bit like Minkowski space. M is taken to be a positive constant and represents the mass of some central object. Well, we've undoubtedly all seen this metric many times. The problem is interpretation of this metric. Although Schwarzschild wrote it down in 1916 as a solution to the Einstein equations, and it was tested, I guess the first time in 1919 properly, with starlight bending by the sun, its true nature was not really understood till about 1963. And that's because if you stare at this metric, you will see that there are some issues with it. The issues have to do with this factor 1 minus 2m over r. You'll see that at r is equal to 2m, this term here blows up, and so the metric is singular. Einstein thought that the fact that the metric was singular was somehow pathological, and indeed many people have really until, well, quite recently, certainly within my memory, also thought that the thing was pathological and made no sense. The singularities at r equals 2m can be removed. They're just coordinate singularities, like the singularity at the origin of plane polar coordinates. It's also singular at r equals 0. At r equals 0, this blows up, and you have no idea what to do. This singularity turns out to be unremovable. It's not a coordinate singularity. So you might ask, how can you ever tell the difference? The problem is, of course, that quantities are tensorial in nature, and of course the value of a component of a tensor depends on what coordinate system you used. It could be absolutely anything. So it really isn't good to try and use components of tensors to determine whether or not you have a coordinate singularity or something worse. What you can do, however, is to use scalar quantities, because scalar quantities will not depend on the coordinate system that you use. And if you did that, you could say, well, I'm going to look at, say, R, A, B, C, D, R, A, B, C, D. That's a scalar quantity. And if you evaluate that in the Schwarzschild metric, you will discover that this looks like some number which I can't remember, divided by times m squared over r to the 6th. So that tells you immediately that something terrible happens at r equals 0. The curvature becomes infinite. It's not infinite at r equals 2m, but that's not a sufficient reason to believe that it's not singular there. What you'd actually have to do is to construct a transformation that takes you to a sensible coordinate system, given that something bad is happening. So this is a hint that this is terrible. Well, this makes it a certainty that this is terrible, but the fact that this is finite only hints that this is a coordinate singularity. We're going to be interested in considering the causal structure of the Schwarzschild metric, and as such, life would be easier if we constructed null coordinates for it. This is kind of easy because we can exploit the spherical symmetry of the space-time. I suppose actually we should say something about the symmetry of this space-time while we're at it. If you solve the Killing vector equations, you'll discover 4 Killing vectors, 3 for rotations, and 1 time translation. But I'm going to put time in inverted commas for a reason that will become obvious. If you work out the isometry group, it's just going to be SO3 times R. So exploiting the idea that the thing is spherically symmetric, the simple way to do this is, and we're going to do this for some other space-times too, so I'll just do it in general. ds squared is equal to minus v, some function of r, dt squared, plus dr squared over v, a function of r, plus r squared d omega 2 squared. The way to construct a null coordinate is to say that u is equal to t minus some function of r, and ask yourself what that function should be. It's sort of similar to what we did in Minkowski space. So every time you see dt, you write du plus f prime of r dr, and substitute into here, and you will get ds squared is equal to minus v du plus f prime dr all squared plus v over, plus dr squared over v plus r squared d omega squared. Null coordinates are going to be such that if you put the null coordinate theta and phi equal to a constant, it's a null line. So let's look at that. This thing here. Multiplying this out, you'll get minus v du squared minus 2v f prime du dr plus dr squared into 1 over v minus v f prime squared plus r squared d omega 2 all squared. So if this thing is equal to 0, that's what you need. If you fix u, theta and phi, then this is 0. You fix u, so that term is 0, that term is 0, and the whole thing will be 0 if this is 0. So that tells you to pick f prime is equal to 1 over v. Then the line element takes the rather simple form. So that's rather nice. You'll see now that wherever v is equal to 0, nothing singular happens to this metric. That is to say, no metric component blows up. The metric is equal to this. And its determinant is not 0. So it's invertible. Its inverse has no component that blows up, except at r equals 0. And also along the polar axis, but that's trivial. So this metric is perfectly non-singular whenever v is equal to 0. So by constructing these null coordinates, one has got rid of the coordinate singularity at r equals 2m. So that's easy. All you've got to do is to do an integral, and then we know what u is. We can relate u and t to t and r. So for the case of the Schwarzschild metric, this is really easy. You just do a single integral and discover that f of r is equal to r minus 2m plus 2m times the logarithm of the modulus of r minus 2m plus an arbitrary constant. writing an arbitrary constant here is fine, but it's not conventionally what you do. Typically you think of R as having dimensions of length and M as having dimensions of length. Remember that G is equal to 1, so that makes that M has dimensions of length. And here you've got an R minus 2M, which is dimension full but sitting inside a logarithm. The argument of logarithms had better be dimensionless, the more so that you've got a 2M here. So you typically take this constant away and stick a 2M there, so that this thing really does look much nicer. So this thing really looks dimensionless. Remember that the modulus sign comes from integrating 1 over x. The integral of 1 over x is not log x, but log of mod x. So we have a rather beautiful picture. U is equal to t minus r minus 2m times this minus 2m should not be there. Where in the world did I put that? Somewhere or other, I had this written down. I think it'd just be a plus sign there. So that's how to relate U to T and R. So having done that, let's try to draw a diagram of the UR plane. Point out that these ideas are first due to Eddington and Finkelstein. Eddington was in 1928, but nobody really believed him, and it was revived by Finkelstein in 1957. So let's try and look at the UR plane. So let's make R go in this direction. Time goes upwards, but really U is a null coordinate. So the nice thing to do would be to put lines of constant U to look something like this. So these will be lines of constant U. And we're looking at the metric ds squared equals minus v du squared minus 2 du dr plus r squared d omega squared. This bit doesn't really matter to us. So the first thing to notice that if v equals 0, that corresponds to r equals 2m. Let's make r equals 2m be there in this picture. It tells you that if you fix r for all u, ds squared is equal to 0. So that's interesting. That tells you that a light ray will go up r equals 2m. So this line here is null. A very long way away from r equals 0, v is tending to 1, and you just get what you'd expect in flat space. So you know that the light cones will look something like just sort of untipped over objects that look like this. You also know that lines of constant u are null. So these are light rays going out in this direction. Let's draw lines of constant r in this picture. Lines of constant r we should probably put in a different color so that we can actually see it. So lines of constant r are going to look something like this. Let's put a bit more of these white lines in here, more u equals constant. So you can see that this line r equals 2m divides the space-time up into two regions. The light cones over here, sort of by continuity, must look like this. But when you get to, say, somewhere like here, they start to tip over, and they just sort of look like that. And out here, they don't look like that. They look just like in Minkowski space. So this is telling you something strange. Suppose that you are sitting in this point in space-time, somewhere here. What will you do? Well, you've got to move along a time-like line, so that means you've got to be in the interior of the light cone, which means that you have got to be expelled from this region r less than 2m. So if a time-like line starts inside r equals 2m, it must leave that region. So at first sight, that's very strange. So this is the diagram really of the UR plane, but not using the Penrose type of conventions, but just simply a picture of what the UR plane looks like. The Penrose diagram would require us to make all lines that are null at pi by 4 to the vertical, so that light cones always went up and down. So we can draw a picture of that happening, and you'll end up with something which looks like this. For R large and positive, everything just looks like Minkowski space. And what we've seen here is that at R equals 2m, something becomes null. So in fact, there will be a region that looks something like this. Remember that a light cone here will look like that. And you can see that on this surface, if you were down here, you would be compelled to cross this surface here. So this line, let's call this line 1, corresponds to this line here. And if you're well away from r equals 0, so r is large, then space-time is asymptotically flat. You would have a nice picture of scri plus, a scri minus, an I0, an I plus, sorry, an I minus, and an I plus, just like you would have done it in Minkowski space. But something bizarre is happening here. If you try to draw lines of constant r in this picture, let's do that in orange so that it corresponds to this orange. Out here, lines of constant r look just like they would in Minkowski space. But this is a line of constant r. Here, all these lines are time-like. On the surface r equals 2m, it's null. And if you think about what happens for r less than 2m, these lines become space-like. So for r less than 2m, lines of constant r you should not feel surprised by that. This has come about because if you thought about the original metric, which is minus v dt squared plus dr squared over v plus r squared d omega 2 squared, then at r equals 2m, v changes sign, so that tells you that this has become a time-like direction, and this has become a space-like direction. So yes, indeed, these things turn over. You can continue to decrease r till you get to r equals 0, where you know something really bad happens. So I'll draw that as a line which looks like this, the wiggly line, which is a curvature singularity. So that's the kind of picture that you get. There is this region which you must escape from. Now, one obviously bizarre thing about this is that this metric here, it's static, and therefore, if you send t to minus t, it doesn't change at all, whereas there is no time reversal invariance of this metric, so you know that you have missed something out. And it's kind of obvious what one has missed out. We derived that f prime squared was equal to 1 over v squared. So in actual fact, f prime is plus or minus 1 over v. And so there is another possibility, which is that you can construct an advanced time coordinate which was equal to t plus r plus 2m times the logarithm of the modulus of r minus 2m over r. In which case, the line element will be of the form ds squared is equal to minus v d little v squared plus 2 dv dr plus r squared d omega squared. So now we can look at the VR plane. Well, it's exactly like the UR plane, but basically the other way up. Here is r going out in this direction. This will be r equals 2m. Lines of constant r will look something like a sort of spray of things looking like this. Well, let's draw lines of constant v first. It's kind of easier. Lines of constant v will look like this. lines of constant r will look something like this. The light cones out near infinity will look something like this. But as you get close to r equals 2m, you can see that the light cones will look something like this. Precisely the time reverse of the situation that we had before. So that if you were sitting inside r equals 2m, and you had to move along in a causal direction, you could never get out of this region. You always have to go further in. So this shows you a boundary of a region that you cannot escape from. So that's a picture of the advanced time versus r and theta. So it's going to give something which is the mirror image of this, the reflection of this in some axis around here, and it will give you a region that looks something like this. And again, if you draw lines of constant r in this picture, they will look like this. I deliberately have not joined these things up. So the light cones here in the Penrose diagram look like this. And you can see that if you get yourself into this region, you can't get out. Worse, if you are here and you want to move in a causal direction, you will inevitably reach the singularity. So inside that region, you will necessarily fall into the singularity. Which means that we ought to understand what is meant by the singularity. Well, in classical general relativity, the only way that you can interpret this is simply as the boundary of space-time. This is very bad, because if you are here, you will reach here after a finite amount of proper time, at which point time will end. I have no idea what that means. I don't even know if it's true. It's a classical concept. The curvature has become very large, and you don't know that somehow such behavior would be wiped out by quantum mechanical processes. So you really don't know what to make of this. So it's a big unknown. So quantum effects may change that picture. I think it's fair to say that one simply does not know. It's quite a challenge. It's a little bit worse than that, because suppose you were here, we agreed that there was points here where you'd be forced to move into this region. But if you are here, you must have started off at the singularity, whatever that means. This surface here, if you think about it, represents part of the boundary of the causal past of Scri plus. but it's not at infinity. In Minkowski space, the boundary of the causal past of Scri plus was just simply Scri itself, which was uninteresting. It didn't really exist. This thing is sometimes called the horizon. And in fact, it's a black hole horizon. The formation of black hole horizons in many circumstances is inevitable. But you're still faced with this thing. This thing, I suppose, is the boundary of the causal future of Scri minus. It's sometimes called the white hole horizon, being the opposite of black. They don't seem to exist. We don't see regions of space-time from which things come pouring out, so it is generally felt that these things don't exist, but these things do exist. Of course, the reason that this happened to us is because we wrote down the Schwarzschild solution, which was independent of time, and in particular was time reversal invariant. So it's a static space-time, and so we should expect that if you reverse the direction of time, you get back to where you started from. So it's probably a consequence of assuming staticity that gave rise to the white hole horizon. Still, from this picture, it looks like something is missing, and I think probably we should complete that in the second lecture this afternoon. So let's stop there for today, for the moment.